we're calling those LDAs. And finally, what are the potential applications of mid and long duration storage? In particular, we're curious about their ability to contribute to reliability in a decarbonized system. And you're going to see a lot of results with regards to that. The study output will include a public report, which is inclusive of analysis and summary of stakeholder feedback and key findings. And with that, I think I'm passing it to E3. Thanks again for being here.
All right, thanks, Tom. I am Andrew D. Benedictus, a director at E3. Folks who are at the first session will recognize me from them. Also, folks who have participated in some of our mini interviews may recognize me from those too. So similar to the first session, I will be taking us through the first couple pieces of digging into what we're actually getting out of our study today, and then I'll pass it over to my colleague, Liz, who will handle the reliability piece as we get to it. I'll note up front, we spent a lot of time in the first session on the first two study tasks, looking at sort of what storage is deployed today and candidate technologies for mid and long duration going forward. So we're going to do a pretty quick touch on each of those pieces today and really focus in on the reliability piece, as Tom already mentioned. So we'll try to keep a pretty good pace going through this first part. We do, before diving in there, want to just highlight some of the emerging findings that we're getting as we go through this. So, this is a series of things that we'll be talking through in more detail as we go through the slides today, and certainly that will appear in our report also. Given that we're going to be digging into a bit more detail on each of these today, I encourage folks to sort of wait on questions. If you have questions, I just get to these at a very high level right now, because I think we'll probably answer a lot of those questions as we dig in a bit on each of these. But just to sort of hit the highlights to start out, give people a sense of what's coming. In terms of that first study question that Tom talked about, the state of storage today, what we're seeing is that most storage deployed today or planned today is small, front of the meter and lithium ion. And what we see as we look into business cases, which we'll show in a moment, is that storage is really leaning on state policy, state programs for profitability. And we're basically not seeing longer durations projects, in part because the way that current programs are set up, there's no real mechanism in there to encourage durations longer than about 4 hours or so. As we go to slightly longer duration, think about mid-duration projects. We are classifying those as sort of the 4 to 10 hour range. And, we talked in the last session about technologies that we expect to be coming online for that. And again, we see that current policy doesn't really put those in the money. And so we're not really seeing those proposed today, but we still do expect a lot of value from those mid durations as there's more opportunity for energy arbitrage, as more renewables come on, and as short duration sort of flattens peak as much as it can, and we start to see the need for flattening beyond just a few hours. But in the meantime, those mid-duration technologies have trouble competing with the short duration ones, which have generally higher round trip efficiency and lower cost today. Moving on to the long duration side of things, I think we sort of tell the same story at first, which is that there isn't really policy out there to support these right now. We're not really seeing a lot of installs right now, or any sort of in the demonstration pilot phase with these technologies. Aside from pumped hydro, which of course is out there today and already exists in the state. And so again, today there aren't real immediate needs to have these real long durations on the system, but we see the future need for them. And so we want to make sure that we're setting ourselves up to be able to meet this future need as it comes. And in particular, as we get to the last bullet there, we see long duration storage being able to provide significant capacity value to New England, especially given the high levels of renewables, in particular offshore wind that we expect to be installed here. storage really benefits from the sort of peaky load shape that results from a lot of intermittent resources on the grid, as it can take advantage of overproduction for charging and fill in the lulls with discharge. And we have at the right-hand side here a little Venn diagram, which I think shows sort of the sweet spot for long duration storage that we expect to hit in the future, which is that you need this combination of supportive decarbonization policy, right? So something that says you can't just run your fossil peakers to meet capacity needs. High renewable penetration, again, as I just mentioned, the ability to basically charge during overproduction and then fill in the gaps. And then, of course, just also, the technology needs to be cost competitive. If instead hydrogen is much cheaper, or synthetic natural gas, or another resource that can provide similar value is much cheaper, then we would see that serving most use cases instead. So, we see the need to sort of hit that sweet spot in the middle, and we expect that the state will get there based on policy goals and how we see this all unfolding. I do want to give a shout out to feedback that we've received so far. As Tom pointed out, you can be emailing him. We'll have a Q&A at the end of this session. We've also been conducting a number of stakeholder interviews. We've done something like 15 or so group interviews so far, engaging dozens of stakeholders in that. So I want to thank everybody who's participated so far in those. We've been learning a lot. It's been very, very helpful. And so we really appreciate the time folks have taken already to provide comments and sit in interviews. I won't go through this slide in great detail, but we're definitely seeing some key points rising to the top in these. Here, I'm really just addressing feedback that we've had relative to the sort of state of storage today. Liz will talk to feedback we've gotten on the more long duration cases later. But we're hearing about information asymmetry being a real issue, right? So just EDCs, MLPs, developers not having sort of visibility into what everybody else is thinking, where things could be most easily deployed, when peak hours will happen, et cetera. So maybe some need for more coordinated planning, or at least more transparency there. We're hearing about how conservative assumptions in terms of battery operations make interconnection difficult, and also how conservative assumptions regarding availability of revenue streams make financing difficult. And then we've gotten a lot of very helpful feedback on specific aspects of use cases, just benchmarking to expectations of developers, hearing about typical sizing, understanding the wholesale distribution tariff, things like that. So that's all been very helpful. So I think now we're going to get into looking at some of the use cases. So in the first session, we showed this slide, and so I won't spend time going through it today, but I did want to bring it up as a reminder to say that when we're looking at the economics for storage today, we've developed a dispatch model that basically takes in all these different price streams and dispatches accordingly to optimize battery revenues, and then we're able to compare that to our cost curves, which we've developed based on public sources. And again, happy to talk more about that in a Q&A, but for now we're just going to skip forward and get to the actual results. We shared some early results in the last stakeholder meeting. We've gotten a lot of good feedback and updated those. And so what we'll do today looking at results is basically start sort of at the large scale, right? Start with our transmission connected big systems and work our way down closer and closer to load and sort of smaller and smaller scale. So starting out, we're looking here at a 50 megawatt 4-hour lithium ion battery. This is a standalone battery, transmission connected, installed today. And on the left-hand side, we'll see a bunch of these cost benefit stacks in the next few slides. So on the left-hand side of that panel, we've got our benefits, things like federal incentives, ancillary services, wholesale energy, clean peak credits and capacity, and then compared on the right-hand side to the costs, including capital costs, warranty augmentation, property tax insurance, fixed O&M, interconnection. And then on the right-hand side of this slide, what we see are the year-by-year annual revenues that give us that levelized benefit stack that we're seeing on the left-hand side of the slide. So a couple things to notice here. One is that even taking advantage of all of these benefits and stacking them together, we can come out net positive, but it's not a guarantee. It's pretty close. But I think we are starting to see more sort of optimism along these lines from developers. We're starting to see projects like this show up in the queue. So I think people are seeing the federal incentives and taking advantage of the state programs and thinking that these projects will work out. In terms of the year-by-year revenues, we talked about this in session 1, but we see ancillary service basically dropping out of the benefit stack after a few years as the market saturates with batteries that can provide that service. Similarly, the clean peak credit price drops off much later in time, but as we just install more and more storage as that program is set up to have that price decline as more comes online. And then as that drops away, what we see as sort of the dominant piece of the benefits becomes just wholesale energy revenues, and those increase as we see more volatile hour-to-hour prices with more renewables installed in the system. So given those evolving price streams, it's interesting to, in this one example, look at our dispatch in sort of a near term and longer term example. So here we're looking at dispatch for that system we were just looking at in 2023. This is just an example week. And in the bottom here, what we see are our clean peak dispatch windows shown, as these sort of like high price periods that the battery can take advantage of. And accordingly, the battery is really just seeking out hitting each of those windows in its dispatch behavior on the top there. So we're discharging during that clean peak window and then charging during the allowed clean peak periods, early morning or sometimes midday. That behavior is completely different as we get up to 2040, where the clean peak prices have dropped down to 0 and our energy prices have become more volatile. So I'll note here, we do use the AESC annual average energy forecasts, but what we do is we add shape to those forecasts based on the renewables in the CECP portfolio builds. So we're doing some hourly shaping because that that hourly price signal is so important in actually determining the wholesale energy revenue that a system can get. And so what we start to see, especially in sort of these middle days here, is that duck curve that we hear about from California and places with a lot of solar online, where we're getting really depressed midday value and good charging opportunity there, and then high prices as the sun goes down, load ramps or net load ramps, and prices go up. And so accordingly, our dispatch behavior is a little less predictable. Definitely shifts to try to cover that late afternoon peak period, and charging opportunistically as the energy prices allow. So moving from there to, instead of a transmission connected system, a distribution connected system. The big change of the story here, and we'll start on the left-hand side of this figure, this is basically the same sort of system, smaller, distribution connected, but our sort of per kilowatt benefit stack looks about the same, except the one thing that's really dropped out is the wholesale energy revenue. And what's happening there is that these distribution connected systems are charging on the wholesale distribution tariff, and basically the cost of charging there is much higher than if they just have access to wholesale energy prices. And so the net revenue of sort of charge discharge against energy prices drops way down, and pushes this into net cost territory. One thing that developers can and definitely have been doing to fight that is to pair with solar. So this is basically the most common installation that we've got out there today, and still a lot of what we see in the queue are these solar paired distribution connected systems. And in this case, pairing with solar gives access to the smart storage adder, which provides a big benefit and can push things back into profitability. I'll note, whenever we are showing these solar plus storage examples, the benefits and costs that we're showing are just the incremental benefits and costs of adding storage to that system. Right, so this is sort of the impact on top of the solar, and not the combined impact of the solar and storage. So zooming in further, getting closer to customer load, we also look at behind the meter use cases. And in this case, on the left-hand side, we're looking at commercial industrial sort of installation. On the right-hand side, a residential one. And again, as with that last example, both of these are paired with solar. So keep in mind that we are looking at just the incremental costs and benefits associated with having the storage in there. What we see on the commercial side is that we get a lot of benefit from resiliency, just avoiding loss of load events, and a lot of benefit from arbitrage of the retail rate structure, right? So a large chunk of demand savings in there. This customer is able to basically manage their demand charges really well by moving load around. On the residential side, both of those opportunities kind of drop out. The value of lost load for residential customers is much lower than a commercial customer, certainly than an industrial customer. And also right now in the Commonwealth, there aren't any available TOU rates for a residential customer to take advantage of rate arbitrage, and so that we don't see any sort of demand savings and energy savings there. So this, to me, points to the need for residential rates that better reflect cost of service in the state. I will point out though, this costs higher than benefits here doesn't mean that a residential solar plus storage system is not net beneficial. This just means that the storage component, sort of incremental to the solar component, is a net cost, but it can still on the whole work out to be net beneficial. While we have this tool out, we did want to look at some longer duration use cases as well. So what we're looking at here on the left-hand side is the same thing that we saw in the very first use case. So this is our 50 megawatt transmission connected utility scale standalone battery. And I have that here just for comparison to the right-hand side of the figure, where we're looking at a very similar installation, 50 megawatts transmission connected, but this one is 8 hours of duration. And we also push it out to the 2030 install year to take advantage of some cost declines that happen between now and then. A couple things that I want to point out here. One is just that, that longer duration, even with cost declines between now and 2030, does really increase our capital costs. So not too surprising, but definitely noteworthy. And the thing is that the benefits don't really increase commensurately with that. In particular, we point out that the clean peak dispatch window is only a 4-hour window. So those extra 4 hours of duration that this 8-hour battery has don't really get it anything as it's participating in that program, which is, for the 4-hour battery, the largest chunk of the benefits. Obviously, that chunk also decreases just because we're looking at a later install year and the credit prices come down. But even if we were looking at the same year, we wouldn't see any sort of growth to that chunk of the bar with our longer duration. So, what we're seeing here is basically that, as we saw with many of the use cases, the state programs are really propping up the benefits and making these cases profitable when they are. But the state programs aren't really designed for longer durations, longer than 4 hours, just based on sort of the current peak needs. And as a result, we're not really seeing a profitable use case for these mid-duration ranges right now. So that was the set of use cases we wanted to go through. I do want to talk for just a couple minutes through some other mid and long duration use cases that we're considering before passing off the reliability side of things. So, we've said this before, but we'll say it again. Our review and analysis really suggests that the key use case for long duration storage is capacity value, right? So we'll dig into that in the whole section that's coming next. And I'll note also that we've heard that in interviews with stakeholders also, right? Long duration developers are really focused on that use case in particular. We do, as a part of the report, want to dig into some other end user applications for mid and long duration storage. So, I won't go into these in detail today, but I do want to note that in the report, we'll be discussing the use cases here and doing some partial quantification of them where appropriate. And these sorts of use cases are things like backup for sites with high value of lost load, pairing with something like Flizzr to provide backup power to a community, for example, that can't evacuate during severe weather. Also thinking about batteries as sort of a faster solution when new infrastructure build is required for interconnection, kind of bridging to that infrastructure build. And then also thinking about the possibility of avoiding demand charges for fleet charging for electric vehicles. But I do want to note this last bullet here that, we think it's unlikely that many of these use cases will really turn up, mostly due to sort of the lack of need for long duration in them and cost competition with shorter duration and other technologies. So, in terms of the sort of chasing lost load, without really aggressive policy that says you can't run fossil fuel emergency generators, then those are just going to be a cheaper solution most of the time, if not all the time. And so that's a hard thing to compete with. They're infrequently run, so the carbon impact isn't high, and they're pretty cheap and they're out there today. But we'll see how the numbers actually play out there. And then the other thing is just that a lot of these use cases may benefit from storage being around, but may not necessarily need the sort of 10-hour or longer range that we talk about when we think about mid and long duration. And so we think that short duration, with its lower cost and high round trip efficiency, probably wins out in a lot of these use cases that are closer to the end user. And I'll close with this one slide showing basically how those costs play out. So the past session, we shared our short duration costs and talked about the sources of those. So I won't go back through that, but I just wanted to throw up our longer duration costs here, which we're taking from the Long Duration Energy Storage Council. And basically these ranges are meant to represent a range of technologies that are expected to be cost competitive over the next several years. So we see here the impact of the IRA in there and sort of dropping off towards the end of the time period shown. And really the takeaway that I want to point out here is just when you only need 4 hours of duration, you're just going to install a 4-hour battery, right? The cost there is really much cheaper when you only need that shorter duration. And it's only when we have use cases that specifically need longer duration where, we'll start to call on those actual technologies. And so I think that's a good segue to a use case where we really will need long duration, which, as we've said many times, will be for reliability. So I'll hand it over to Liz now.
Great. Can you hear me okay?
Yep.
Okay, perfect. So thanks, Andrew. And of course, thanks to Tom and the team at Mass DEC and DOER. We're now going to turn to the third objective or question in this study, which is assessing the potential reliability contributions of storage resources in Massachusetts. I'm going to just note a couple of things up front. One is that we're focused here on resource adequacy. Andrew talked about other types of reliability, potentially behind the meter on the distribution system or related to resiliency. Those will get addressed in different ways separately in the report, but the focus of the analysis that we're doing here is on the ability of the system to have sufficient generating capacity to meet loads across the range of weather and system operating conditions. So what we would call resource adequacy. As we organized in the last section, what I'll do is first briefly address some of the key feedback that we received or questions, remind you of our approach, and then talk through the electric sector reliability challenge and the role that storage can play in supporting that resource need, both in 2030 and then in 2050 as the system evolves to its highly decarbonized end state. So you can jump to the next slide. So before we dig into the analysis, just to briefly address a few pieces of stakeholder feedback. One is I'll note that based directly on stakeholder feedback, we are evaluating portfolios beyond what was shown in the state's Clean Energy and Climate Planning, or CECP 2050 portfolios. So you will see that in some of the results, a broader range of renewables, and we have even more sensitivities that will show in the final report. Second, we agree with stakeholders who would say that, the optimal portfolio of storage is going to be a function of the loads and the rest of the portfolio, and you should rerun a capacity expansion model. However, the scope here is designed to be consistent with many other ongoing state planning efforts that are also a function of that CECP 2050. So rather than undertake an exercise that would re-optimize that full portfolio, we're really focused here on the value streams that storage can provide, rather than a specific optimal allocation across storage types. Now, the third thing I'll note is that given the scope and timing of this study and uncertainty regarding federal hydrogen policy, we're not addressing it quantitatively in this particular study. It's very complex, as many of you are aware. We recognize that storage is a very valuable part of seasonal storage in the power sector, and we'll talk about it qualitatively, but point to future work or other efforts to address hydrogen in detail. And then I'll note one point on data here, which you'll also be able to see when we summarize the inputs, is that E3, the reason why we use the raw NREL data, for those of you who are sort of more technically oriented, rather than the ISO New England's variable energy resource profiles, is that our modeling requires the ability to match weather data from loads to renewable output. So we have benchmarked our profiles so they look very close to ISO New England's, but we are using the underlying NREL data, for which we also have weather data. So you can go to the next slide. So as a very brief reminder, E3 is using a loss of load probability model to assess the ability of storage to provide effective capacity or capacity to meet the reliability challenge in New England. This is a loss of load probability model, and it's used by utilities and jurisdictions across North America. I think the important feature here that I want to call out is that we're simulating both loads and available resources on a sequential 8760 hourly basis across a year under, and then we do that thousands of times to represent a range of weather and system outage conditions. And so by doing that simulation, thousands of times, we are able to identify periods in which the system is at risk of loss of load. And then we can evaluate in a robust way the ability of storage to fill in those gaps where there is, what I'll call relative resource insufficiency, and support the reliability of the grid. You can go to the next slide. So in the first stakeholder session, we spent some time talking about the load data. So I'll spend less time there, but just focus on the renewable data. The load data comes from the state's planning efforts, but we have taken an hourly 2011 load profile, including a base system and the electrification loads as they vary from 2030 to 2050. And we've simulated what those same loads would look like, so the same end-use demands under 39 weather years of data. And then we match that load data to renewable output profiles that are derived based on robust NREL databases. So we have a wind speed generation database as well as a solar radiation database. I'm sure many of you are familiar with these. And we have hundreds of points, onshore as well as offshore for offshore wind, for which we can generate average generation profiles. So just as kind of a summary of that data on the right, on average, we get a capacity value of around 22% for solar in Massachusetts, That's assuming a tracking system, about 38% for onshore wind and 47% for offshore wind. You can jump to the next slide. So what I'm going to do over the coming slides is first identify what the reliability need is, and then talk about the ability of storage to fill that gap. So in 2030, New England, under a future consistent with the CECP 2030, will remain summer peaking, but renewable additions have started to shift that summer peak from the late afternoon into the evening. So, you know, with a peak of 31 gigawatts, we can see that's relative, you know, that's already quite an increase from today's, you know, 25% increase. And on the left here, what we have is what we'll call the net peak. So that top line being gross load. And then if you subtract out the expected renewable generation during these few sample days, that's going to drive, you know, when the system is most at risk of loss of load, or essentially the sort of net load or the remaining resource need. So on the left, we've just pulled an example challenging day that is going to drive that, you know, resource need. But on the right-hand side, you know, I just mentioned we have this, you know, we use a reliability model. Here is what that resource need looks like when we simulate the system hundreds of times. And we can see that, you know, really clearly it's a summer evenings from 5 to 7 p.m. are when there is the greatest gap, you know, between all the renewable output you're getting and the remaining load. And that's going to drive when you have the highest loss of load risk. So resources that can generate during that period are going to have, you know, higher capacity value. And of course, this is, you know, I will note in 2030, there is already expected to be a lot of renewables on this system, you know, somewhere on the order of 30 gigawatts, you know, with particularly a lot of solar built out in the near term, aligned with that planning effort. All right, can you go to the next slide? Now, storage can support the system both in the summer and in the winter in 2030. The top two rows, and I recognize there's, you know, a lot of data here, so I'll kind of try to give you a little bit of time to take this in. What we're first showing is just the overall dispatch of the system, where that solid line is the gross load and the dotted line is the total generation. And, you know, the reliability challenge weeks, in this case, the reliability challenge week is a week when wind is particularly low generation relative to its, you know, average over the course of the year. It's something like 15% of all generation over the course of the year, but when it's not generating, it is driving the high risk periods. Storage is actually having to charge here from a, you know, the marginal thermal resource or an import to discharge during that net peak hour, which has shifted, you know, from 4 to 6 p.m. On the right, we've just called out what that charging pattern looks like. So the dark green indicates when the storage is charging in the morning and into, you know, what would be the duck curve in the middle of the day. And then storage is discharging in that net peak period in the evening. So the, you know, the top row, that is the summer reliability challenge. That's when the greatest reliability, that is when the greatest resource insufficiency exists. And so that's where storage is providing value. It's going to drive its ELCC value. Now, it's also supporting the system in the winter, even though it's slightly less pronounced here. So the gross load in the black line on the lower left shows that the needs are a little bit flatter, but more sustained during the day and then peaking in the evening. And there's more support by offshore wind, even in this challenging sample that was pulled. So to support the system here, storage is again charging from thermal generation or imports, given, you know, that's what's on the margin, and then it is discharging into that evening peak to support that evening peak, which is around 6 p.m. You can go to the next slide. And all of this is going to inform the ELCCs that we ultimately estimate. So I'll next show you what the system looks like in 2050. So in 2050, New England is significantly winter peaking, with the reliability challenge being clearly into the evening. The same framework as previously applies, where the reliability need is going to be driven by the net load or gross load less renewable output. But the load shape is now different. We have a lot of electrification load that has materialized, and the resource mix has also evolved. So, the peak here is going to be over 50 gigawatts, more than double today and now in the winter. And the gross load is going to be spread over multiple hours that are needed to support electrified heating and transportation. The gray load, so the gray here is going to show that remaining resource need after we've subtracted out renewable output. While this, is going to vary week by week, you can see here that the offshore wind in particular has really shown up, and there's a lot of generation from offshore wind. So there's about 36 gigawatts on the system in these base scenarios shown. So they're generating somewhere around a third of all of the output on the system. But there still is these remaining stretches, which, given the high sustained loads, are longer. And when you simulate the system hundreds of times, rather than just look at these, example challenging days that are indicative of all the challenging days we see, you can see that there is high loss of load risk in the coldest winter months, as you'd expect, between December and February. And it's most pronounced in the evening particularly between 6 and 9 p.m. or, maybe a little bit earlier, like 4 to 8 p.m. Sorry, shifted that a little bit. And then you also see it occur in the morning. So these are going to be opportunities for long duration storage to fill, or longer durations of storage to fill these sustained periods of high loss of load risk. So if you want to jump to the next slide, thanks, Andrew. So first we can look at the summer. While we know this is not where the reliability challenge occurs, it is where we see storage supporting the grid. The solid line, again, is going to be that total demand or load. And the dotted line is going to represent the full dispatch of renewables. By 2050 in the base CECP portfolio, this is 100 gigawatts of renewables, and we'll show some cases, if you think that lower levels of renewable output are expected, then, we can show the impacts that it has on reliability. But the kind of key point here is if you look at all of the output, the solar in yellow, the offshore wind in light blue, and onshore wind dark blue to a lesser extent, there's really ample resources on the grid for storage to charge from, and then support that evening high remaining peak, basically when the solar stops generating and you need to serve that remaining net load. And just to note, all of these graphs will be available online, so you can kind of dig into each day in detail. But what you see on the bottom, and you can kind of match to the top, is that the green is when in our model the storage is charging, and then it discharges in the purple periods, so filling that that gap in the net peak in the evenings. Great, you can go to the next slide. And okay, so again, here we're, sorry, back a slide. Yeah, there we go. So this is, arguably, I think, one of the most important slides, because in 2050, that reliability challenge is in the winter. And here, this is what's going to drive the overall reliability need on that system. The top line is showing the load again, and then the total generation before curtailment is that the dotted line above that. And you can see, even with all of the renewables on the system, in the challenging weeks, there is still generation output that needs to occur from thermal resources to fill in those low renewable periods. I wanted to call out, so in those circles there, you can see later in the week on day 5, where there are cases we see in the data here where even in 2050, given the lack of renewable generation in the most challenging winter weeks, storage resources need to charge from either thermal or imports in order to basically recharge to then discharge during that net peak in the evening. And this is particularly true during these multi-day low renewable output stretches. And so that's what we've called out here as just one of those examples. Great. Now you can go to the next slide. So what does this all mean? So effective load carrying capacity, or ELCC, as I've referred to, is that ability of a resource to contribute to the total effective capacity needs of the system. So basically to meet demand throughout the course of the year, subject to whatever your reliability criteria is. So when we calculate an ELCC, what we're doing is calculating the perfect capacity equivalent of each resource. In this case, we're focused on storage, but you could do that for any of the resources on your system. And this allows you to evaluate them on an apples-to-apples basis in terms of their ability to reduce all of those gray bars on the previous slide, so the periods of relative resource insufficiency or resource need after you've dispatched. So for example, just a generic resource with a value of 50% ELCC would mean that 100 megawatts of that resource's nameplate capacity would be equivalent to 50 megawatts of some theoretical perfect capacity value. And I also just wanted to note, as noted on the figure on the right, this isn't just a way to value the contributions of intermittent renewables like wind and solar, or energy or duration limited resources like shorter durations of storage, but also applies to thermal resources or any other form of demand response, hydro, et cetera, that you put on the system, as a function of variables, ranging from fuel security to seasonal temperature derates or outage rates, et cetera. But for this study, we're really going to focus on storage. Okay, you can go to the next slide. So I just, before showing the results, also wanted to call out the kind of key characteristics of what a storage ELCC will look like. So it's going to be a function both of the penetration of that resource on the system and the duration of the resource you are adding to the system. The reason it's a function of the penetration is something called the saturation effect. So as more of that resource is added to the system, as you can see in this picture on the right, it's going to clip that peak. And the remaining resource need, or the remaining net load curve, is going to flatten out and be longer. And it's going to extend the period in which the system needs a resource to dispatch in order to lower further that peak. And so, as you flatten that net load curve, successive tranches of storage are required, and they're required to dispatch over longer periods in order to have the same effect over the entire remaining net load period. So, incremental builds and longer durations are going to be needed to fill the gap. And you can go to the next slide. And then a second important feature, and I think this will be noted many times as you look at the results and also look at the overall report that comes out of this study in the fall, is that storage ELCC is not a static number. It's a function of the rest of the portfolio. And, particularly for long duration storage, it's going to be a function of the amount of offshore wind on the portfolio. So, that's because the shape of that net load is going to drive the ELCC value. So here we've just pulled a week from 2050. On the top, you could see that we have 3 tranches of offshore wind totaling around 30 gigawatts. And they shift that net peak out of the late afternoon and into the rest of the day. So here, the total amount of shifting that they're able to do is worth about 4 gigawatts, moving it, I think, from day 2 to roughly day 7. But this is, I will say, a particularly low output week for offshore wind, which capacity value is often much higher. I'm just saying for this specific example week, here's how much it could help the system. But then if you were to separately look at that system and look at storage, it would be able to clip the peak about, in this case, successive tranches totaling about 20 gigawatts, clip to the peak around 15 gigawatts. And so, when we report the numbers, we'll report them over the course of the entire sample period. But here we're just pulling an example week because it's useful to show that third row, which is the diversity benefit. And essentially what happens is that the wind on the system creates a narrower net peak, and then storage is better able to clip the remaining amount of resource need. And thus, when you combine them together and reorganize the storage, you actually are able to shift down the remaining need or the sort of net peak more than the sum of the individual parts. And this is that diversity benefit. And so the more offshore wind, the implications for this study is that the more offshore wind on our system, the higher ELCC storage will have. And we can, show this in different ways. You can go to the next slide. So now I'll show you the actual ELCC estimates. On the left-hand side, we're showing the ELCC on the 2030 system. And what we're showing is, starting with 5 gigawatts on the left, relative marginal to a system with no storage. And then the second tranche is an incremental 5 gigawatts, and moving, to the right is more in 5 gigawatt increments, how much that the incremental ELCC value is. So what you can see here is that, for about 5 gigawatts in 2030, you have essentially perfect capacity. The only reason it's driven down slightly is because of the assumed forced outage rate, which we're using a forced outage rate for storage at 10%. So the marginal ELCC starts to fall after that 5 gigawatts as the existing storage on the system has, as shown in the previous sample days, it's basically flattened out that net peak such that new storage added to the system can't fully can't further flatten or mitigate that remaining flatter peak load. Now in 2050, as you see on the right-hand side, all of that electrification load has materialized, and there's also a lot more renewables on the system and more renewables relative to firm capacity. So storage is very valuable, particularly, as we said, in shifting, shifting both solar and renewables for this short duration storage. So the 4-hour resource here is getting, almost perfect capacity through 10 gigawatts before it starts to decline. And you'll see we have a range here because we have modeled the system under renewable build-outs that go from 40 to 60 gigawatts of solar, 11 to 30 gigawatts of offshore wind, and 9 to 11 gigawatts of land-based wind. Now, the the ELCCs do start to decline after 10 gigawatts, but it's really driven by, that is driven basically by storage's inability to dispatch over very long periods. And so it doesn't start to decline until further out. Great. So we can, I'll also show you, the 8-hour and the long duration. So great. So now here again, we have the 2030 values on the left and 2050 on the right. And we're looking at a representative 8-hour resource. And so when you look at the 8-hour resource, you know, starting in 2030, we can get almost twice as much of that resource added to that system in 2030 to support the perfect capacity needs, as with the 4-hour resource, before it starts to decline as the remaining net peak really starts to flatten out. And there is less from storage to, there's less basically for storage to arbitrage, so to renewables to charge from and then to discharge to flatten out that peak. And after you get beyond that 10 gigawatts, it falls very quickly, largely because that net peak flattens so much. You know, it's a much smaller overall system that you really need a much larger duration in order to fully discharge over a full period and actually reduce that peak further. Now in 2050, we have a much higher gross load, but also much more renewables on the system on the order of 100 gigawatts, as I mentioned earlier. So for these CECP 2050 portfolios, you can get, you know, nearly 20 gigawatts of mid-duration storage with perfect, you know, the ability to provide near perfect capacity, the adjustment based on, again, so for the 10-hour, for the 8-hour storage, we also assumed a 10% forced outage rate. And there's two primary reasons, basically, why it does start to fall. So, you know, there becomes, so it basically starts to fall as it starts to flatten out that net peak again. But it's much later given, you know, much higher loads. Great. Okay, so now we're looking at the ELCCs for long duration storage. And here we've modeled a generic 100-hour resource with a 50% round trip efficiency. And we've layered it onto a portfolio that has not just renewables, but it does have some short and mid-duration storage on the system under the assumption that those resources will have been built first. So in 2030, the system is smaller and again, like other resources, the narrow peaks, basically that long duration storage fills in what it can on these narrow peaks. But then after 10 gigawatts, it starts to decline because there is less remaining windows that long duration storage needs to fill, as well as less renewables on the system for it to charge from. In 2050, there is a larger sustained peak, and that's going to create these opportunities for long duration storage. And in particular, there is a lot of offshore wind on the system, which both, as we said, sort of narrows the peak and provides these windows for offshore wind to discharge, as well as provide opportunities for charging. So, you know, when you have 100 gigawatts of renewables to charge from, there's, you know, a lot to support the long duration storage on the system. But as you can see, because long duration storage is still around at that 20 gigawatt or more incremental nameplate capacity, you know, at that 20 gigawatts, it starts to become very sensitive to the amount of renewables on the system. So if you have a much lower renewable output, and again, this is still 40 gigawatts of solar, even 10 plus gigawatts of offshore wind, and about 10 gigawatts or 9 gigawatts of land-based wind. It has much less renewables to charge from and much longer remaining resource need gaps to fill. And so its ELCC declines a lot faster. And then I'll note too is that that white dotted line is if we just restrict the land-based resources. So in a scenario in which only land-based wind and utility scale solar are reduced, for example, due to land constraints, that has a much less effect on the ELCC of long duration storage than when you do the lower bound, which actually restricts the amount of offshore wind. And this is because of the large complementarities of offshore wind and long duration storage, as we showed in those illustrative figures previously. It's also because offshore wind is providing something like a third of the generation on the system and significantly supporting the system and creating these windows in which long duration storage can discharge for a shorter range of net peaks, so of remaining resource need. And so I think what to take away from that is that the ELCC of long duration storage is going to be highly dependent on the ability to build offshore wind. But if you can build that offshore wind, even at 20 plus gigawatts, you get a really high ELCC value from long duration storage. But it's again going to be really contingent on having 100-ish gigawatts of renewables on the system. You can go to the next slide. So this is just very briefly showing that long duration storage, it's the same data shown as you pull out theoretical perfect capacity. So on the left side here, what we're showing is in 2030, under the base case, if you, for example, remove 5 gigawatts of perfect capacity, it's 5.5-ish, almost 6 gigawatts of long duration storage needed to replace it and maintain the same level of reliability. But as you go out further, so at 15 gigawatts of perfect capacity removed, so that's, if you think about it, more than 15 gigawatts of thermal capacity retirement, it would take over 80 gigawatts of long duration storage to replace it. By 2050, that replacement value is much higher, but it is a function of the amount of renewables. So in that base case, with the 100 gigawatts of renewables, you can, replace almost 20 gigawatts perfectly of perfect capacity. And then, but if you don't have as much renewables on the system, then that number starts to decline, and you need basically more than double the amount of long duration storage to replace your perfect capacity. Great. So this is a subset of the broader set of results. And if you want to flip to the next slide. So, we recognize that it's a lot to take in. So what we've done here is introduce, some of our base sets of results. But in parallel, we're working on several related sensitivities, including sensitivities in which there are no imports. The CECT modeling that we are drawing from assumes 12 gigawatts so that's nameplate of imports. And we assumed that by 2050, around 8.5 gigawatts are firm. If you reduce that number of imports or at an extreme remove them, and those come from, both Canada and New York, that removes a major source of a resource in which long duration or short duration storage can charge from. We're also looking at contingencies related to the loss of offshore wind. So if you lost the transmission to offshore wind, as well as loss of transmission to points north, and then looking at 100% renewable cases that have even higher levels of renewable build out. We're also working on a broader set of outputs related to some of the reliability statistics or metrics, curtailment numbers, and emissions numbers. Great. So thanks very much. I will turn the mic back to Tom.
Great. So just to close folks out, next slide, please. Just want to remind everyone of the timeline, you know, like where we've come from, where we are, and where we're heading in the next several months. So to recap where we've come, the study kicked off at the end of March, and you know the bulk of the content generation for the report, like the modeling, the analyses that you've seen today, stakeholder engagement, that's been taking place since then. Today, as we've been doing with many of you already, we hope to continue to gather your feedback on these results, which is very critical to generating a quality and relevant study for the Commonwealth. Through the rest of August, we'll be conducting a final round of stakeholder interviews. So if you haven't heard from us yet and want to meet with us, please get in touch. If you're interested in connecting with us on that, we're going to be also finishing the analyses and receiving your written comments. E3, from there, we'll finalize the report in early fall. And then with that, DOER will draft its report required by the legislature and deliver to them, the legislature, by year's end. Public comment on the DOER report will commence thereafter in early 2024. Next slide, please. So immediate next steps, kind of like I just said, seeking continued stakeholder engagement. Please get in touch with us. You can email me if you're interested in having an interview and you haven't heard from us yet. Also, we can submit any written comments that you have, and we strongly encourage you to do so. Submit those to me by Friday, September 1st, 2023. And then the last two bullets, a reminder of where you can find the webpage for the study, and that a recording of today's session will be made available and posted on the website, hopefully later today. Next slide. And with that, I think next slide, that basically brings us into Q&A. I think before we start the live Q&A, I just want to see if there are any questions in the chat that haven't been answered yet. It looks like there's about 4 or 5. Maybe we can, let's just start, maybe we'll take these live rather than kind of maybe typing the answers out. So starting with Jennifer Burke's question, how would the results differ? Maybe Jennifer, do you want to unmute and just ask your question?
Yeah, sure. Can you hear me?
Yeah.
Hi. Sorry, mistyped. So I guess I had an earlier question, which was, you know, did you guys model or look at what the maximum duration would be to get 100% ELCC? I know that requires kind of multiple iterations, but that's kind of a general overarching question, and you know that's the first question that was kind of answered. And then the second question is, you know, if you do that, you know, how did you model any technology with, you know, higher than 8 hours, like a 10+ hour duration system with a higher round trip efficiency? Because it looks like you did the 50% for the 100 hour and kind of nothing in between. So that's kind of the next question. Thank you.
Liz, you're on mute.
Sorry, can you hear me? Okay, great. So we didn't model a, here's what the maximum duration that you would need to completely fill the resource need, but that is something that we could look at in our model and basically see what the size and the longest size of those gaps are on the system. So that's something we could get back to you on the exact number. And then in terms of round trip efficiency, so we modeled 3 representative resources. One is a 4-hour resource with a 90% round trip efficiency. One is an 8-hour resource with an 80% round trip efficiency. And then one is a 100-hour resource with a 50% round trip efficiency. If you think that we should add a resource, you should send me an email, because that's the type of thing we can evaluate in our sensitivities. So, and you know, another intermediate resource like a 20-hour resource, you know, with an intermediate round trip efficiency, So we benchmark those to generally the technologies we're seeing out there today, but we haven't in these results included another technology.
Yeah, no, I definitely think it would be helpful, and I'll send the follow-up email to do a resource. So one, to kind of figure out for each of the different scenarios what the maximum duration is. So that would be great if you can do that. That's kind of an important signal, I think, to the market. And then the second piece on, figuring out kind of a different or modeling that second resource at the 80% round trip efficiency for a higher duration. Because it's not, 8 hours is a little bit arbitrary. So if it needs to be 12 hours or 10 hours or 14 hours, that would be really good to know. There's no reason that those types of technologies can't scale up, because they're usually technologies that can easily scale their energy. So I think that would be very valuable. So I can send a follow-up on that. Would I send it to the Thomas Ferguson
Yes,
email?
that's great. And
Yeah.
I'll get it to the appropriate folks.
Great. And this is, so this is Jennifer Burke with Lockheed Martin. Thanks.
Thank you. We have one more question in the chat, and then like I just put in the comments, after we address this last question in the chat, just please raise your hands for further questions, and we'll take them in the order that they're received. But for this question in the chat, I'm going to ask Dana Gubiak to unmute.
Hi, Tom. Thanks.
Hi.
Just looking at the ELCC slides, it seemed like the capacity that would need to be online, or at least is ideally online by 2030, is roughly 40 gigawatt hours for MDES, and anywhere, depending on duration, I don't know which one was modeled, anywhere from 60 to 500 gigawatt hours of LDES. This is operational by 2030. So I was curious if there's been a study on the supply chain itself to see, are there enough suppliers to meet that capacity by 2030?
Yeah, I think that's a very good question about how you might actually implement the portfolio and build out these resources in time. And that's something we've been evaluating through a series of interviews with mid and long duration storage developers, and getting their perspectives on the extent to which the supply is available and what is the status of existing projects. I think that the targets are ambitious but aligned with what the state is planning for. And so we are modeling sensitivities that say, if this can't be met, here is what the capacity value of these resources are. And we will be able to also inform that supply chain question to some extent through these interviews and our own sort of desk research, though this isn't a detailed supply chain study.
Great. Now turning to the hand raise, I think Louis is first.
Thank you, Thomas, and thanks for all of these kind of sharing these results on the studies. I also, looking at the ELCC, especially the slide 32, where you're showing kind of that positive effect with the renewables. I was thinking about 37, where you're looking at further work. They're kind of combined of something I was going to throw out there for your thought is whether or not, especially when you look at the 100% renewable situation, you might want to consider having excess renewables, and that having renewables in your system, obviously, since it improves your LDES, ELCCs or these types of pieces, since there's a positive effect, looking at renewables above the assumptions might be places for you to look at what kind of positive impacts those have, what kind of how they might point to goals for the renewables to get there, because often renewables can substitute for excess storage, especially in 100% renewable situations. So maybe my question is, what was the percentage of renewables of overall load in your 2050 case? I think I knew this when it was going through ISO New England study stuff, but I can't remember it now.
Yep. So so I'll say two things. One is that because we simulate the system under many years of weather conditions, the numbers vary a little bit based on the weather year on the average years. solar is about 35, 36% of generation by 2050. Offshore wind is another 35% of generation. Then there's around 10% coming from onshore wind, 10% from transmission, and then the remaining is nuclear and hydro.
And you say generation, but energy, right? That's the energy basis?
Yeah.
Yeah, so definitely when you're thinking about, I'll make the suggestion, maybe we'll try to join an interview or whatever, but definitely when you're looking at that case of 100% renewables, you may want to have excess renewables as it making it cheaper for the overall system, rather than the large amount of storage that you would end up needing for that exactly 100% case. Thanks for all the work.
Thank you, Louis. Seth, please unmute and ask your question.
Yeah, thanks for all of this. It's been very interesting. Yeah, I had a question that I typed in around load flexibility. It sounded like that was not a consideration here. I'm just wondering if there can be some analysis done around the potential for load flexibility. I don't know what all the assumptions are around electrification, but I imagine, I'm sure, well, certainly the winter heating is a big driver for the winter peaking, as well as EVs. EVs in particular, there's a lot of flexibility in charging profiles for that, and there can be considerations around preheating buildings in winter months and pre-cooling buildings, or lowering or raising set points. So I'm wondering if there's any room in the analysis for some of that flexibility consideration.
Yeah, I can also speak to that. So when you think about load flexibility, so I will note that we are using the state's EV load shapes for electric vehicles in particular, and there is some assumption around some management of that charge over time, but it is static within our model. And the way we think about it is that load flexibility in many ways substitutes for storage, right? In the sense that either one can be used. You can either move your load or you can move your supply to meet the other. And so if you think about adding systems with higher amounts of load flexibility, then you will need less storage, generally speaking. But we can definitely provide, let us take away to think about, what a scenario would look like that includes higher levels of load flexibility.
Thanks. I think if it's not in there, just pointing out that flexibility can substitute for storage in many cases as potentially a lower cost solution would be great just to highlight in the report. So thanks.
Thanks, Seth. Chris.
Yeah, hi, Chris Jilka from Daymark. In terms of simulated battery dispatch for short duration or medium duration resources, what are the unit commitment parameters around storage for day ahead versus real time? Like for example, is there an assumption that most batteries would bid into the day ahead market?
Yeah, that's a good question. So in our dispatch that we have modeled here, we're really more focused on sort of the day ahead. And so we'll admit there freely, I think we're probably undervaluing a little bit. It's a bit of a conservative view because there is room in the real-time market to, do that sort of just-in-time adjustment and get more revenues there. But of course, when we're just building sort of a simple 8760 dispatch model, that's a harder thing to capture. So, there's, yeah, I think in these results, it's a little bit more day ahead focused. I think we're sort of missing out on some of the real-time market revenues that that folks might be able to get.
Yeah, that's a tough call. Yeah, it's a good answer. Yep, so thanks for that.
Yeah, and I'll just note there, we actually have looked at the sort of real-time versus day ahead, revenues in other studies, and we've generally found, a bump, but a small one. So, we think there is some conservatism to what we're doing, but we don't think it invalidates, the results in any way, or that it would really swing economics one way or the other.
Great, thank you.
Thanks, Chris. Samer, you're up.
Yeah, and Andrew, I apologize. I joined late. I just wanted to confirm the concerns that we highlighted about both the location and operational schedules of energy storage. And if you don't put them in the right locations, or if you don't operate them correctly, and the third one, which was the uniqueness of the distribution system, that a city and a town have very different characteristics. So all of that plays in, and that if you don't do it the right way, energy storage is actually detrimental to the system and not helpful. So did you highlight that in the report?
Yeah, so we didn't really get into that much today outside of just mentioning the concerns and necessary conservative assumptions that make interconnection difficult, but certainly in the report we're highlighting what you just talked about, right? The sort of very detailed distribution level view that's sometimes necessary to understand how beneficial or not, and yeah, those operational considerations. So those are, we didn't really get to them today, but they are in the report, and it's been really helpful to hear from you more about that.
Perfect. Yeah, because I think it's very important to understand that you can't just throw storage on the system, because and you can't expect it to operate in the right way.
I also saw a question that I wanted to just clarify the answer to around the dispatch. This is on the ELCC piece around the dispatch plots shown. The original capacity comes out of the CECP study, but the dispatch is based on our own modeling of how that system would operate across a range of weather conditions. So it's not the dispatch from the state's capacity expansion modeling, it's from E3's 8760 modeling of that system over many iterations of weather conditions.
Dave Wilby.
Thanks, and thanks for the presentation today. And I think Samar's question sort of addressed what I was going to ask, which is just to the degree there's been some thinking as part of this around location. And I think what I just understood is that there has been, it just wasn't covered today. So
okay,
if I understood that correctly, that answered my question. Thank you.
Thank you.
And I'll maybe just add a touch of color to that, which is that it's hard to model something like that, because that's really getting much more into the implementation side of things, thinking about specifically where things can go, and specifically how the values and costs change there. So that step is I think, as you're pointing out, as Samar pointed out, as others have said, a pretty detailed one, and one that's hard to capture when we're doing this sort of statewide or even ISO-wide analysis. But certainly a really important consideration. And in the report, we'll speak to that and talk about the ways that can sort of change the picture. But I think, analytically, without really getting deep into the implementation piece of things, that's hard to capture.
Josh.
Hi, can everyone hear me okay?
Yep.
Okay. Hey, I'm Josh Ghost with Cypress Creek Renewables. Could we go to the slide that has the ELCC curves, and maybe we can look at the short duration slide, I guess. Apologies, I don't have the number. Yeah, this one. I guess I'm a little confused on how to interpret this slide. So taking a look, I guess, at the 2050 one, I guess the label incremental nameplate capacity is, I guess, what is confusing me. So is the graph saying that in 2050, on top of your existing portfolio, when you add 2,500, like that 2,500 megawatts is coming at 90% ELCC values? And so if that's the case, is it ignoring the portfolio that was already online, so the ELCC would already be lower? An explanation on how to interpret these charts, especially the 2050 ones, would be helpful.
Sure. So the way to think about it is for each tranche, it's incremental to the previous tranche. So the first 5 gigawatts would have, that 90% ELCC. The next 5 gigawatts so among that next 5 have an average of 89% ELCC. The next 5 gigawatts beyond that, so the incremental 5 gigawatts have an ELCC of 72, and then building up from there.
Okay,
and
thank
so,
you. Yeah, go for it, sorry.
Oh, I was just going to note that we start from a system with zero storage, and then we add it on and look at the ELCC of the incremental additions.
Understood. In the final report, is E3 planning to put out like the ELCC values for the years that you're looking at, like not the incremental, but like what is the ELCC of storage in the system?
Yeah, like the average of the full portfolio on the system
Correct.
in that year. Yeah, we do have that number. Yeah, exactly. We do have that number. It's not in this, but it will be in the report.
Is it possible to like see that sometime with E3 share those before the final report comes out so that stakeholders could comment on that?
Sure. If you send me an email, I'm happy to, or send it through Tom. We're happy to share that number, and we can chat with Tom about whether or not there's a way we could, add it as an appendix slide or something like that to this deck. But we do have those numbers.
Understood. Thank you so much.
Yeah, and I just dropped my email in the chat for folks.
This is, maybe I'll just want to clarify
Sure.
here. This is Arnie Olson from E3. Just I thought it'd be useful to clarify at this point that when you're looking at these ELCC values that are projected out over time, is just to understand that each of these is a function of the specific portfolio that's assumed to be online in future years. And as Liz, emphasized, a big part of the high value for long duration storage is the fact that there's so much wind that's assumed in the portfolio, which changes the shape of the net load and provides energy for charging. So just that note of caution when you look at future ELCCs, that they will move around as the portfolio moves, and they're specific to the portfolio that's online at the time.
Sarah.
I think that's a perfect leeway into my question, I hope. My question is whether the E3 model responds to the addition of various storage durations by sort of shifting the total resource needs. So is it adjusting how much resources you need overall as you add storage? So therefore you're kind of getting that feedback in the optimization. And if the answer is yes, are you seeing values in the different storage duration classes in sort of total resource savings? Does my question make sense? I think I'm asking it correctly, but I can clarify.
Yeah, so you can see them both compete or complement each other. So in these cases, for the short and mid duration, we start with a system that has no storage on them, because if you started, for example, adding 8-hour storage, which is probably in practice what will happen, to a system that already has 4-hour storage, it will have basically filled out those peak periods, and the remaining net load, so kind of the gray figures of all those previous graphs, will be harder to meet with a resource that is similarly, less than, say, whatever the remaining net peak period is. So even like a 10-hour resource, it can compete with each other. The resources can complement longer durations of storage, like 100-hour duration storage, because they're basically filling out, the different parts of that remaining net load curve. And so it can be that longer duration storage is supported by there already being some short duration storage on the system. And so in the report, we do have some of the tables that show some of those interactive effects.
Can I just clarify? My question was, thank you. That's helpful. Also, it was whether it affects other resources, not just other storage resources. Does it change the amounts of, either renewables or other types of resources that are expected to be on the system in 2030, 2050?
Yes, so we are not rerunning a capacity expansion with different inputs than previous to say, if there is more storage forced into the model, how much renewables do you need to build to complement it? But what we will be able to show is there is going to be a capacity value associated with wind by itself, capacity value of storage by itself, and then the value of that diversity benefit on average in our portfolios as you build out the two separate portfolios.
Thank you.
So I
Maybe
see
just to
where,
clarify, just quickly there, that when you see us calculating ELCC values as percentages of nameplate, though, those will typically be calculated as a one-off for that individual resource based on an underlying portfolio. All the diversity benefits that Liz mentioned, those exist within the entire portfolio, but we usually, for a single resource, calculate its individual ELCC.
Okay, so I see we're a couple minutes over. Great discussion. Thanks everybody for really thoughtful questions. Again, thanks so much for joining us today. The slides and recording of this presentation will be made available on the study website, hopefully later today. We'll also send out an email to the stakeholder list, kind of summarizing kind of the key next steps, obviously including contact information. So do you have any questions or want to schedule time to talk to us about the study? And yeah, just thanks so much for joining us today and look forward to continued engagement.